Question number 8. A metal M belongs to S block. So S block being you should know now. And it burns with a yellow flame. Okay. So what is burns with a yellow flame? Normally flame test, it is sodium. So in the presence of excess oxygen, it gives a solid M1. So sodium with oxygen, it should give NO2 O2, Na2O2. On treatment with cold water, so Na2O2. Why it is Na2O2, not Na2O? So you should know that. This theory, you know, from lithium, sodium, potassium, rubidium, and cesium. You should know from potassium, rubidium, and cesium, they are more or less forming the superoxide. They are familiar with superoxide. And when you go to peroxide, you need to understand sodium is the dominant one forming the peroxide. That is why it is Na2O2, not Na2O. Lithium forms dominantly oxide. Okay. So with lithium, it will be Li2O. With sodium, Na2O2. With potassium, KO2, RbO2, CSO2. Those are the dominant ones for each element. Okay, so on treatment with cold water, M1, which is M1, Na2O2, gives a clear basic solution. So you need to understand this will give basically NaOH, that is the basic solution. And they say solution gives a basic M solution M2 and a covalent compound. So, okay, so basically it will give NaOH and a covalent compound. We will see what could be the covalent compounds. Think about this. There is O2, 2 minus. So what is this covalent compound that is going to form? Okay. And this is called M3. From this covalent compound, M3 is going to form. And they say M3 reacts with acidified Ag2O, give a colorless diatomic gas. So again, they are telling what is going to happen. Silver is going to reduce and H2O2 will be oxidized basically to form O2 gas. And M4 excess of M2 reacts with metal T to give a colorless diatomic gas M5 and a water soluble compound. Okay. So this could be very straightforward to explain to you because this gives you the idea from the first point that you can automatically understand and identify what is the element, that is sodium. Then you need to understand the oxide is Na2O2, which is going to form NaOH when reacted with water, and the covalent compound H2O2. And when this is reacted with Ag2O, the Ag will be reduced and O minus in the -1 charge will be get oxidized to O2, and which will produce M5, which is our hydrogen gas. And M6, what is M6? Can you tell what is M6? Here. So water soluble compound. The addition of HCl dropwise to an aqueous solution of M6 gives a white gelatinous precipitate. So you already know what is that white gelatinous precipitate. But they say M2 reacts with metal T. What is M2 here? We already know now. M2 is we get it from the basic solution, that is NaOH, and reacts with metal T. So we don't know what is metal T yet, to give a diatomic gas M5. So what could be T? Can you think what could be T? So it is a metal. I'm waiting for your answers. What do you think? What could be T that gives you a diatomic gas M5? So this should be a diatomic gas M5, and T should react with NaOH in order to give this diatomic gas. Normally, when you think about reaction of NaOH with like let's say like non-metallic compound, for an example sulfur, it will form Na2S or Na2S2O3. There will be no gases formed. The common element that form this gas with NaOH is amphoteric one. So this could be aluminium, which forms sodium aluminate, NaAlO2, plus the gas is hydrogen. Okay. So it says colorless diatomic gas and a water-soluble compound. So this is our water-soluble compound. This is M6 here in this case. Okay. So when this is M6, the addition of dilute HCl dropwise to an aqueous solution of this one gives a volatile precipitate. So you know NaAlO2. So there is NaAl2. When you add this, it will form aluminium hydroxide, which is our white gelatinous precipitate. This should be the white gelatinous precipitate M7, which dissolves in excess acid, and M7 does not dissolve in diluted ammonia. So you can imagine what is happening with diluted ammonia. So aluminium hydroxide will be present in dilute ammonia. But when you try to make it excess, so it will form the anion with OH minus, okay? Not with ammonia, with NaOH here. Identify M1, M2, M3, M4, M5, M6, M7, M7, and T. So the first point was easy because you know it should be sodium. And when it reacts with oxygen, you should be familiar, Na2O2 is formed. And the next point is on treatment with water, this Na2O2 will react with water to form sodium hydroxide, and the covalent compound is O2, 2 minus, which is H2O2. And when it is oxidized with Ag2O, it will form basically O2 gas, which is the diatomic gas here. And excess of M2 reacts with metal T. So basically metal T is aluminium, which gave you hydrogen, which is M5 here in this case. And water soluble compound M6 is sodium aluminate, NaLO2. And you add this HCl dropwise and to form this hydrolysis having the aluminium hydroxide, which is our white gelatinous precipitate. And which is not even dissolved in diluted ammonia. So you can understand this. Predict the products of the reaction M1 with hot water. So you know what is M1 here. So M1 is presence of excess oxygen. So it is Na2O2. So you can write down the reaction of Na2O2. So Na2O2 react with hot water. Na2O2 with hot water. Because here in the description, it gives like M1 cold water, it gives a basic solution and a covalent compound, which was H2O2. So Na2O2 with cold water gave NaOH and H2O2. Now what they are asking here is what is going to happen when it reacts with hot water. Remember, with hot water, it will give NaOH, same compound, no problem in that. But here it was H2O2, but here this is O2. Okay, as you can imagine. Okay, that is given. So this is one of another informative question. So we have many informative questions. So this is a good place where you can learn many things, how to approach. Okay, this type of question should be approached in this way. So you need to understand. Since this is the only point, the only difficulty that you can have here is identifying T, because if you are not familiar with NaOH reaction with the elements, normally metals, you can't connect metals to NaOH because they are already basic and these are basic. So you need to try to go with nonmetals, but you need to know when these nonmetals react, they will not produce this gases. So you can think about an amphoteric compound, which is aluminium here. Okay. Question number 8, part B, a crystalline ionic inorganic compound Q. So you have given a molecular weight. So you can basically write that. So we have a crystalline solid with molecular weight that is given just for informations. And when heated, gently releases a substance which turns anhydrous copper sulfate into blue. So basically it tells that this compound when heated will release water. That is why the anhydrous turns blue. Okay, and 3 tests were carried out to the aqueous solution of Q, and the tests and observations are given below. So what are the tests and observation? So they have added diluted HCl. The solution turned turbid. Okay, so think about the reaction of anions with dilute acids. So which one normally gives a turbid solution? So gives a turbidity with evolution of a colorless gas. So if you can remember about some compound where it gives some turbidity plus a gas, and burning magnesium ribbon in this gas gave 2 solids. So okay, and now yellow in color. So one of the solid is yellow in color. So think about this. At this point, it should be familiar with to you what is this anionic compound, because when you think about this observation, normally when you add dilute acid, for an example, we know there are many compounds like carbonates, bicarbonates, nitrites, sulfides, sulfites, but all those gives gases, true, but only one compound that gives a turbidity plus a gas. So if you remember about thiosulfate, when you react it with H plus, HCl, or any other acid like a dilute acid, so this gives sulfur and SO2 gas. So they are talking about this thiosulfate here. So you know what is here. This is thiosulfate. And they have added AgNO3 solution dopewise, so a white precipitate, and it turns black on heating. So you should know what is actually happening. When you add AgNO3 to thiosulfate, it forms Ag2S2O3, and when it is in solution, it produces Ag2S. That is why it turns black on heating. And also it is very similar with the lead nitrate also. So PbS2O3, then it turns into PbS. Okay, and they have to identify Q, draw the most acceptable Lewis structure for its anion. So we have to draw the Lewis structure of anion, which is S2O3 2 minus, but we have to find this Q. So think about this. They have given this sodium, the molecular weight of sodium. So automatically you should think about what type of molecule is this. So basically, you know, this should be Na2 S2 O3. So this is sodium thiosulfate. But don't forget the first point. They say when it heated, water is given out. So it should be some X H2O. So you have to find this X also, right? Based on the molecular weight. So if you think sodium is 46, then sulfur it is 64. Oxygen we have 48 here. Then here it is 110, 118, 158 basically. Okay. Then when you subtract this 248, the entire molecular weight, by the 158 here. So 248 minus 158, you will get 90. Okay, so this 90, remaining 90 should be all water molecules. And so you divide it by the molecular weight of water, that is 18, and you will get that as 5. So basically Q is Na2S2O3.5H2O. So that is Q. Then we need to know the, so we know Q is Na2S2O3.5H2O. Then you need to draw the restructure of S2O3. So basically it will be like this. So always remember, when there are two sulfur, one of the sulfur will have mainly zero oxidation state. So since this compound has -2 charge, because when you think about this formula, so here we have 2Na plus S2O3 2 minus. So surely there should be two negatively charged oxygen. So put the lone pairs, and to complete octet of this oxygen, so it should form a double bond, as well as to complete the octet of sulfur, it should also form a double bond. So this is the typical structure of S2O3 2 minus. Okay, so just to give an additional information, let's check about the oxidation state of each of these sulfur. Okay, so this sulfur bonds to another sulfur where the electronegativities are same. So we can conclude this oxidation state is 0. Okay, then what about this sulfur? So this sulfur, we have -1 and +1. So oxygen is electronegative in this case. So this will go -1, this will have +1. Here it is same, -1 +1. And here each bond will give -1. So -1 +1, -1 +1. So it is +2. So the central sulfur atom here have an oxidation state of +4, right? So this is little bit of additional information that you can take from this Lewis structure. Okay, so moving on. So we will I will share the screen again. So we have drawn the Lewis structure. So light balanced chemical equation for the reaction takes place in test 1, 2, 3. Indicate the precipitates with an arrow in the equation. So don't forget, if they have mentioned what to do, you have to do that. Now here they have said to indicate the precipitate using an arrow. So you don't need to use solid here or show any other thing. You just show the precipitate using arrows. That's fine. Okay. Okay, so what are the reactions? So first we add HCl to sodium thiosulfate. So basically Na2S2O3 with HCl will give NaCl. So I will stop, I will share the screen. Okay, so we have NaCl. So remaining is H plus with S2O3 2 minus. So it will give sulfur as one of the product, and then SO2, and finally water. So this is one of the reaction that is happening with sodium thiosulfate, right? So the next reaction is with AgNO3 and then PbNO3. So it's straightforward again. So when you have Na2S2O3 with AgNO3, so make sure you balance these two. So first thing, sodium nitrate. So it will form NaNO3 plus remaining is Ag2S2O3. So Ag2S2O3. So this is the white precipitate. What it happens here when it react with water principally, it will convert to Ag2S plus H2SO4. Okay. So this is the overall. So this is the black. So you have to show this one. You have to show this one. You have to show this one. So this is the arrow that they are expecting, right? So with PbNO3, it's similar again. So PbNO3 twice then. So NaNO3 and Pb2S2O3 with water. So Pb2S2O3 with water will form PbS plus and H2SO4. Okay, so same reaction, only the reagent is different. So we have this reaction that you need to write. So these are the reactions that you need to mention here in this question. Next one, give two uses of Q. So you know sodium thiosulfate is mainly used as in the identification reactions of iodine in iodometric reaction. So that is one main use of sodium thiosulfate. We use them in iodometric titrations. Okay, so you can write down that one. And also it is used in neutralization of bleaching agents. That is one of the other main uses that you can mention, right? There are many other uses. Even it is used in medicine for antidotes, and even it is used in as to make some compounds for the phosphates. So they have asked only two, so you can mention the simplest two. That is fine. Okay, so this summarizes this part B, and moving on for part C. So this is again a calculation related question. So I will use the board very quickly to discuss this question qualitatively and as much as possible quantitatively. Okay. Right. So the question says, we have a mixture, right? This mixture contains KCl and KClO3, and it's 1.1 gram, and there is an inert material also, right? So what they have done here is they have taken 1.1 gram and they have dissolved in 50 cubic centimeter of water, and they have diluted up to this using 200 cubic centimeters. So they have a 250 cubic centimeter solution, right? So this is why. So from this, what they have done, they have taken 25 cubic centimeter of this solution and they have added SO2 gas. Okay, so when they have added SO2 gas, what is actually happening here? ClO3 minus in this solution is converted into Cl minus. So that is one point. Okay, and they have removed excess SO2 in the solution, and what they have done to this resulting, they have added AgNO3. So you know what is going to happen here. There will be AgCl precipitate. Okay, Cl minus in this solution, that is from ClO3, as well as Cl minus from already present KCl, all will be precipitated as AgCl when combining with Ag plus. And they have found when you dry and all these things, and it was 1.35 0.135. Yeah, it was 0.135. That is one process. And another part of this solution, why this, they have taken 25 cubic centimeters again, and what they have done, they have heated with Fe2 plus solution. So they have given, it was 30 cubic centimeter of 0.2 m, right? Yeah, in the acidic medium, and they have mentioned the volume that is needed to unreacted. So when we add Fe2 plus here into this solution, they have given this following reaction is happening. So what is actually happening again? ClO3 minus is converted to Cl minus, and Fe2 plus will be oxidized to Fe3 plus. Okay, and the remaining Fe2 plus, now some amount of Fe2 plus will react with the ClO3 minus to convert it to Cl minus. So there are some amount of Fe2 plus remaining in the solution. So this will be again, after this particular reaction happening, some amount of Fe2 plus from here is going to remain, and they found this will react with MnO4 minus to find the unreacted amount. So they have given the unreacted amount was reacted with 0.02 m 20 cubic centimeter of KMnO4. Okay, so you know what is the reaction that is happening here. MnO4 minus will reduce to Mn2 plus since the medium is acidic, and you know if the medium is basic it will be MnO2, and again Fe2 plus will be oxidized to Fe3 plus. So this is the normal procedure. Okay, and finally they are telling us to find the percentage of KClO3 and KCl by mass in this initial solution. Okay, so what is the idea from this? Okay, so we will discuss this qualitatively first. So the mixture contains Cl minus and ClO3 minus. The first step of using SO2 makes all ClO3 minus converted to Cl minus. Okay, so after the first step, you know the mixture does not have ClO3 minus, all are converted to Cl minus. So that is why here we can find the total amount of chloride in this solution after the treatment of SO2. And when you find the number of moles of AgCl precipitated, it should contain Cl minus that was given by KCl and Cl minus that was given by ClO3 minus because of the treatment with SO2. So the first thing that you can do is you can find the number of moles of AgCl. So it will be 1.35 gram over Ag is 108, Cl is 35.5. So it will be 143.5 gram per mole. So you know this amount, and this will be equal to NAgCl will be equal to Cl minus from KCl plus Cl minus from KClO3. Okay, so this is a nice relationship that we have, right? So don't forget about this. So you know this, the total amount of Cl minus from KCl and ClO3. So if we find one of these two, and you know total, automatically you can find the other. So to find one of these, they have given the second procedure. The second procedure says, when it is heated with Fe2 plus, only ClO3 minus in the solution is going to reduce to Cl minus. Okay, so which gives the idea from the second step, we can find the amount of ClO3 in this mixture, because here they have given a description stating that only ClO3 minus is going to react. So we can find the amount of Cl minus directly from KClO3, which means we know this one. So we know the total one, we know this one directly, and you can find even Cl minus from KCl. So it will be straightforward. Okay, but we have to do the calculation. So how to do the calculation? First, you have to find the initial amount of Fe2 plus, because Fe2 plus is going to react with Cl minus. So Fe2 plus, Fe3 plus plus 1 electron, and ClO3 minus going to reduce to Cl minus. So 3 oxygen, 3 water, 6 H plus. So 2 minus 1. So I will add 6 electron. Plus 6 minus 6 cancel, minus 1 minus 1. It is balanced. So to find the amount of Fe2 plus that is reacted with ClO3 minus, you have to multiply this first equation by 6. Okay, so this will be 6. 6H plus 6 electron, ClO3 minus. Okay, this is one of the main reaction that is going on. And the other main reaction that is going on is the remaining unreacted amount of Fe2 plus after the addition. So again, there will be this reaction where Fe2 plus is oxidized to Fe3 plus, and MnO4 minus is reduced to Mn2 plus. So again, I need to balance this one. So 4H2O, 8H plus, and 5 electrons. So again, I want to balance the amount of Fe2 plus with respect to Mn. So I have to put 5 here and 5 here. So these are basic things in balancing. Okay. Then we know the initial amount of Fe2 plus. It will be 0.2 m times 30 cubic centimeter times 10 to the power minus 3. So which will give you the initial amount as 6 into 10 to the power minus 3 moles. Okay, so this is the initial amount. So if you can find the unreacted amount, then you can find the reacted amount of Fe2 plus with ClO3 minus. And if you know the reacted amount of Fe2 plus with ClO3 minus, you can find the amount of ClO3 minus. Okay, so that is the idea. So how much that is unreacted? MnO4 minus. So we will react how much, we will see how much Fe2 plus is unreacted. So we know the MnO4 minus amount. So this was 0.02 times 20 times 10 to the power minus 3. So this will be basically 20 into 2 over 100 into 10 to the power minus 3. So we can cut this. So this was 0.4. Okay. Yes, so 0.04 into 10 to the power 0.4 into 10 to the power minus 3 moles. So this is the amount of MnO4 minus reacted. So according to the stoichiometry, you can see 1 mole of MnO4 minus react with 5 moles of Fe2 plus. So you can write unreacted Fe2 plus should be 0.4 times 5 because stoichiometry is 1:5. So this will be 2 into 10 to the power minus 3 moles. So now you know the initial amount of Fe2 plus and unreacted amount of Fe2 plus. So you can find the amount of Fe2 plus here, which is the reacted amount with SClO3 minus. So ClO3 minus will be 6 minus 2. So this will be 4 into 10 to the power minus 3 moles. Okay. So if you know this one, you can divide this by 6 because the stoichiometry is 6:1. So you divide this by 6 to find the number of moles of ClO3 minus that is present, don't forget, in 25 cubic centimeter because this is a 25 cubic centimeter. So you need to back calculate for 250 cubic centimeter. So finally, when you find this amount of ClO3 minus that is present in 25 cubic centimeter, you have to multiply this by 10 in order to calculate for 250 cubic centimeter, which means at the end of this calculation, you know the amount of ClO3 minus that is given from in this mixture. Okay, so you know the Cl minus from KClO3. So you know this one. So this one would be 4 into 10 to the power minus 3 divided by 6 to calculate based on the stoichiometry, and you need to multiply it by 10 to calculate for 250 cubic centimeter. Okay, and at the same time you know this one 0.135 over 143.5 gram per mole, the total amount of Cl minus. But don't forget, this is also for 25 cubic centimeter calculation. You have to multiply it by 10 to get the 250 cubic centimeter calculation. So the only thing that you don't know here is this one. So you can calculate this one, you can calculate this one, subtract this amount from this, you can have Cl minus from KCl. Okay. Now finally we have to do two calculations. One, you know the Cl minus from KClO3. So you multiply this by entire molecular weight of KClO3. And here after the subtraction, you find the mass of KCl. So you need to divide it by 1.1. Finally, mass of this and mass of this. And then multiply it to get the percentage weight. Okay. So this is this becomes very straightforward here for KClO3 mass. You just need to multiply it by the molecular weight of KClO3. Then divide it by the mixture weight, that is 1.1, then multiply it by 100. Okay, so you will get around 74.2 something. Okay, then you need to find the mass from KCl, so you need to subtract this amount here by this first to get the number of moles, then multiply it by the KCl weight, and you will then divide it by 1.1 and multiply it by 100. You will get around 18 point something. Okay, so this is the idea. So when you write this one, it is easy that first you calculate the amount of Cl minus from KClO3 and show its percentage, because that is straightforward. Why? Because you calculate here the Fe2 plus moles that is reacted with ClO3 minus directly. Okay, so you know the direct amount of ClO3 minus, this amount, multiplied by the molecular weight, divided by 1.5 percentage, get the percentage. So that is done. And in the second case, you can find initially the number of moles of AgCl and tell it is the total number given by Cl minus from KCl and Cl minus from KClO3. Then you can write, we already know this one, so we need to find this one. Total number is known, so you can show this equation and find Cl minus from KCl. Again multiplied by the molecular weight of KCl, divide it by 1.1, get the percentage. So you will have two answers nicely. Okay, but don't forget, along with this step, it is very necessary initially to write the entire reaction that is happening. So you need to write this reaction, which is this reaction and this reaction. This reaction is this reaction is this, and finally write down this one as AgNO3 with Cl minus AgCl plus NO3 minus. So then it would be easy for you to write down the following process, which means the calculations. Okay, so this is again a typical question, not hard. The only thing is you have to argue. Okay, that is the idea. Right, so this is basically done. So we have seen similar type of questions in 11, 12, 13, and even 2014. So you all know question number 8, part C will be always like this. Okay, so students get afraid of doing this part. So I have always said, you don't afraid, because these reactions are already commonly seen in previous papers. So here you have additional advantage here in this particular question, because they have given even this reduction, what is actually happening. But even if you don't know this equation, you should be able to think that, okay, so from this step, I should be able to determine the Cl minus from ClO3, or either Cl minus from directly KCl. So if there is a reaction like this, which means it is surely from KClO3, because there should be a reduction. If Fe2 plus is going to oxidize, and a remaining amount of Fe2 plus is reacting with this one. So straightforward this is. Okay.